Section 2 of the ABC of Relativity by Bertrand Russell. This LibriVox recording is in the public domain. Chapter 2. What Happens and What is Observed. A certain type of superior person is fond of asserting that everything is relative. This is, of course, nonsense, because if everything were relative, there would be nothing for it to be relative to. However, without falling into metaphysical absurdities, it is possible to maintain that everything in the physical world is relative to an observer. This view, true or not, is not that adopted by the theory of relativity. Perhaps the name is unfortunate. Certainly, it has led philosophers and uneducated people into confusions. They imagine that the new theory proves everything in the physical world to be relative, whereas, on the contrary, it is wholly concerned to exclude what is relative and arrive at a statement of physical laws that shall in no way depend upon the circumstances of the observer. It is true that these circumstances have been found to have more effect upon what appears to the observer than they were formerly thought to have, but at the same time Einstein showed how to discount this effect completely. This was the source of almost everything that is surprising in his theory. When two observers perceive what is regarded as one occurrence, there are certain similarities and also certain differences between their perceptions. The differences are obscured by the requirements of daily life, because from a business point of view they are, as a rule, unimportant. But both psychology and physics, from their different angles, are compelled to emphasize the respects in which one man's perception of a given occurrence differs from another man's. Some of these differences are due to differences in the brains or minds of the observers, some to differences in their sense organs, some to differences of physical situation. These three kinds may be called, respectively, psychological, physiological, and physical. A remark made in a language we know will be heard, whereas an equally loud remark in an unknown language may pass entirely unnoticed. Of two men in the Alps, one will perceive the beauty of the scenery, while the other will notice the waterfalls, with a view to obtaining power from them. Such differences are psychological. The difference between a long-sighted and a short-sighted man, or between a deaf man and a man who hears well, are physiological. Neither of these kinds concerns us, and I have mentioned them only in order to exclude them. The kind that concerns us is the purely physical kind. Physical differences between two observers will be preserved when the observers are replaced by cameras or phonographs, and can be reproduced on the movies or the gramophone. If two men both listen to a third man speaking, and one of them is nearer to the speaker than the other is, the nearer one will hear louder and slightly earlier sounds that are heard by the other. If two men both watch a tree falling, they see it from different angles. Both these differences would be shown equally by recording instruments. They are in no way due to idiosyncrasies in the observers, but are part of the ordinary course of physical nature as we experience it. The physicist, like the plain man, believes that his perceptions give him knowledge about what is really occurring in the physical world, and not only about his private experiences. Professionally, he regards the physical world as real, not merely as something which human beings dream. An eclipse of the sun, for instance, can be observed by any person who is suitably situated, and is also observed by the photographic plates that are exposed for the purpose. The physicist is persuaded that something has really happened over and above the experience of those who have looked at the sun or at photographs of it. I have emphasized this point, which might seem a trifle obvious, because some people imagine that Einstein has made a difference in this respect. In fact, he has made none. But if the physicist is justified in this belief that a number of people can observe the same physical occurrence, then clearly the physicist must be concerned with those features which the occurrence has in common for all observers, for the others cannot be regarded as belonging to the occurrence itself. At least, the physicist must confine himself to the features which are common to all equally good observers. The observer who uses a microscope or a telescope is preferred to one who does not, because he sees all that the latter sees, and more too. A sensitive photographic plate may see still more, and is then preferred to any eye. But such things as differences of perspective, or differences of apparent size due to difference of distance, are obviously not attributable to the object. They belong solely to the point of view of the spectator. Common sense eliminates these in judging of objects. Physics has to carry the same process much further, but the principle is the same. I want to make it clear that I am not concerned with anything that can be called inaccuracy. I am concerned with genuine physical differences between occurrences, each of which is a correct record of a certain event from its own point of view. When a man fires a gun, people who are not quite close to him see the flash before they hear the report. This is not due to any defect in their senses, but to the fact that sound travels more slowly than light. Light travels so fast that, from the point of view of phenomena on the surface of the earth, it may be regarded as instantaneous. Anything that we can see on the earth happens practically at the moment when we see it. In a second, light travels 300,000 kilometers, about 186,000 miles. It travels from the sun to the earth in about 8 minutes, and from the stars to us in anything from 3 to 1,000 years. But of course, we cannot place a clock in the sun and send out a flash of light from it at 12 noon Greenwich Mean Time and have it received at Greenwich at 12:08 p.m. Our methods of estimating the speed of light have to be more or less indirect. The only direct method would be that which we apply to sound when we use an echo. We could send a flash to a mirror and observe how long it took for the reflection to reach us. This would give the time of the double journey to the mirror and back. On the earth, however, the time would be so short that a great deal of theoretical physics has to be utilized if this method is to be employed, more even than is required for the employment of astronomical data. The problem of allowing for the spectator's point of view, we may be told, is one of which physics has at all times been fully aware. Indeed, it has dominated astronomy ever since the time of Copernicus. This is true, but principles are often acknowledged long before their full consequences are drawn. Much of traditional physics is incompatible with the principle, in spite of the fact that it was acknowledged theoretically by all physicists. There existed a set of rules which caused uneasiness to the philosophically minded, but were accepted by physicists because they worked in practice. Locke had distinguished secondary qualities, colors, noises, tastes, smells, etc., as subjective, while allowing primary qualities, shapes and positions and sizes, to be genuine properties of physical objects. The physicists' rules were such as would follow from this doctrine. Colors and noises were allowed to be subjective, but due to waves proceeding with a definite velocity, that of light or sound as the case may be, from their source to the eye or ear of the percipient. Apparent shapes vary according to the laws of perspective, but these laws are simple and make it easy to infer the real shapes from several visual apparent shapes. Moreover, the real shapes can be ascertained by touch in the case of bodies in our neighborhood. The objective time of a physical occurrence can be inferred from the time when we perceive it by allowing for the velocity of transmission, of light or sound or nerve currents, according to circumstances. This was the view adopted by physicists in practice, whatever qualms they may have had in unprofessional moments. This view worked well enough until physicists became concerned with much greater velocities than those that are common on the surface of the earth. An express train travels about a mile in a minute. The planets travel a few miles in a second. Comets, when they are near the sun, travel much faster and behave somewhat oddly, but they were puzzling in various ways. Practically, the planets were the most swiftly moving bodies to which dynamics could be adequately applied. With radioactivity, a new range of observations became possible. Individual electrons can be observed, emanating from radium with a velocity not far short of that of light. The behavior of bodies moving with these enormous speeds is not what the old theories would lead us to expect. For one thing, mass seems to increase with speed in a perfectly definite manner. When an electron is moving very fast, a bigger force is required to have a given effect upon it than when it is moving slowly. Then reasons were found for thinking that the size of a body is affected by its motion. For example, if you take a cube and move it very fast, it gets shorter in the direction of its motion, from the point of view of a person who is not moving with it, though from its own point of view, i.e., for an observer traveling with it, it remains just as it was. What was still more astonishing was the discovery that lapse of time depends on motion. That is to say, two perfectly accurate clocks, one of which is moving very fast relatively to the other, will not continue to show the same time if they come together again after a journey. It follows that what we discover by means of clocks and foot rules, which used to be regarded as the acme of impersonal science, is really, in part, dependent upon our private circumstances, i.e., upon the way in which we are moving relatively to the bodies measured. This shows that we have to draw a different line from that which is customary in distinguishing between what belongs to the observer and what belongs to the occurrence which he is observing. If a man is wearing blue spectacles, he knows that the blue look of everything is due to his spectacles, and does not belong to what he is observing. But if he observes two flashes of lightning, and notes the interval of time between his observations, if he knows where the flashes took place, and allows in each case for the time the light took to reach him, in that case, if his chronometer is accurate, he naturally thinks that he has discovered the actual interval of time between the two flashes, and not something merely personal to himself. He is confirmed in this view by the fact that all other careful observers to whom he has access agree with his estimates. This, however, is only due to the fact that all these observers are on the earth, and share its motion. Even two observers in airplanes moving in opposite directions would have at the most a relative velocity of 400 miles an hour, which is very little in comparison with 186,000 miles a second, the velocity of light. If an electron shot out from a piece of radium with a velocity of 170,000 miles a second could observe the time between the two flashes, it would arrive at a quite different estimate, after making full allowance for the velocity of light. How do you know this, the reader may ask? You are not an electron. You cannot move at these terrific speeds. No man of science has ever made the observations which would prove the truth of your assertion. Nevertheless, as we shall see in the sequel, there is good ground for the assertion. Ground, first of all, in experiment, and, what is remarkable, ground in reasonings which could have been made at any time, but were not made until experiments had shown that the old reasonings must be wrong. There is a general principle to which the theory of relativity appeals, which turns out to be more powerful than anybody would suppose. If you know that one man is twice as rich as another, this fact must appear equally whether you estimate the wealth of both in pounds or dollars or francs or any other currency. The numbers representing their fortunes will be changed, but one number will always be double the other. The same sort of thing, in more complicated forms, reappears in physics. Since all motion is relative, you may take any body you like as your standard body of reference, and estimate all other motions with reference to that one. If you are in a train and walking to the dining car, you naturally, for the moment, treat the train as fixed, and estimate your motion by relation to it. But when you think of the journey you are making, you think of the earth as fixed, and say you are moving at the rate of 60 miles an hour. An astronomer who is concerned with the solar system takes the sun as fixed, and regards you as rotating and revolving. In comparison with this motion, that of the train is so slow that it hardly counts. An astronomer who is interested in the stellar universe may add the motion of the sun relatively to the average of the stars. You cannot say that one of these ways of estimating your motion is more correct than another. Each is perfectly correct as soon as the reference body is assigned. Now, Just as you can estimate a man's fortune in different currencies without altering its relations to the fortunes of other men, so you can estimate a body's motion by means of different reference bodies without altering its relations to other motions. And as physics is entirely concerned with relations, it must be possible to express all the laws of physics by referring all motions to any given body as the standard. We may put the matter in another way. Physics is intended to give information about what really occurs in the physical world, and not only about the private perceptions of separate observers. Physics must, therefore, be concerned with those features which a physical process has in common for all observers, since such features alone can be regarded as belonging to the physical occurrence itself. This requires that the laws of phenomena should be the same whether the phenomena are described as they appear to one observer or as they appear to another. This single principle is the generating motive of the whole theory of relativity. Now, what we have hitherto regarded as the spatial and temporal properties of physical occurrences are found to be in a large part dependent upon the observer. Only a residue can be attributed to the occurrences in themselves, and only this residue can be involved in the formulation of any physical law which is to have an a priori chance of being true. Einstein found ready to his hand an instrument of pure mathematics called the theory of tensors, which enabled him to discover laws expressed in terms of the objective residue and agreeing approximately with the old laws. Where Einstein's laws differed from the old ones, they have hitherto proved more in accord with observation. If there were no reality in the physical world, but only a number of dreams dreamed by different people, we should not expect to find any laws connecting the dreams of one man with the dreams of another. It is the close connection between the perceptions of one man and the roughly simultaneous perceptions of another that make us believe in a common external origin of the different related perceptions. Physics accounts both for the likenesses and for the differences between different people's perceptions of what we call the same occurrence. But in order to do this, it is first necessary for the physicist to find out just what are the likenesses. They are not quite those traditionally assumed, because neither space nor time separately can be taken as strictly objective. What is objective is a kind of mixture of the two, called space-time. To explain this is not easy, but the attempt must be made. It will begin in the next chapter. End of section 2.